Swayam Prabha. Digital India. Educated India.
Good afternoon, everyone. Professor V. Balakrishnan is a theoretical physicist who has worked in a number of fields and areas, including particle physics, the mechanical behavior of solids, dynamical systems, and quantum dynamics. He is also a distinguished academic known for his deep insights and contributions to this field. His passion for teaching and research has inspired countless students. We are truly privileged to have you here today, sir.
Thank you. Okay. So in this hour and the next, I want to do something. I want to talk about a topic which is very, very important. In fact, if you ask me what I regard as the most important topic of all, no matter what science you do, what mathematics you do, what area of knowledge you are interested in or you pursue, there's one aspect of one mathematical aspect which is absolutely crucial and which permeates everything, cuts across disciplines, and that's the subject of statistics and probability. Probability, more significantly, probabilistic arguments, they play a fundamental role in our understanding of nature. You might have heard that the universe is quantum mechanical. It is intrinsically a probabilistic subject. There are many, many sources of randomness in nature, of which the most profound are two. One is when you put objects at a finite temperature, there are thermal fluctuations in energy, in momentum, and so on, physical quantities. So thermal fluctuations and then quantum fluctuations at a deeper level. These play a fundamental role in our understanding of physics, modern physics, and of all science eventually. So I'm going to talk a little bit about probability theory. It's a mathematical subject in one sense, but it's also a very applied and practical subject in another. So no matter what you do, it's a good idea to know a little bit of statistics and probability so that you can, go ahead with the subject. It will look like mathematical games, recreational mathematics, but I assure you that it's got very serious purpose behind it. So we'll start with a little game, then go on from there, and I'll show you how it's got physical applications as we go along. And this has to do with tossing coins. So I'm going to assume that we have n coins, or one coin tossed n times, it doesn't matter. And if I toss these coins repeatedly, there are two possibilities out of each toss. Each toss can land with the heads or tails. And I'm going to denote heads with H and tails with T. Those are the only two possible states of the coin after you toss it once. Either it's a head or it's a tail. Now, what is meant by saying that the probability of a head is a half? What is really meant by that? You're all familiar that there's an even chance if it's a fair coin, not a biased coin. We're going to work with biased coins very soon. It's a generalization. But if it's a fair coin, the common statement that you learned right from the beginning is the probability of a head is equal to a half, that of a tail is equal to a half in a single toss. What is really meant by that?
So the difference out of the n coins that are tossed, n by 2 should be heads, n by 2 should be tails.
Is it going to be exactly n over 2?
Not n by 2, but like as you said, you toss it repeatedly, indefinitely.
Right.
Out of that, roughly n by 2.
n by 2 coins tosses will turn out to be heads. Is that what you're saying?
Sir, can you please repeat?
How do you define this probability? What's meant by the half? Where does the half come from?
Out of the two possible states, we're asking for one, sir. And that one is denoted by the half. 1 by 2.
Why not anything else?
Because, sir, there are no other possible states, no other possible samples.
That's a good point, but I'd like a rigorous definition of it. I mean, operationally, probability is a measure in mathematics, but we're not going to get into that aspect here. What is an operational definition of the probability? Number of favorable outcomes. So let's focus on heads. For me, head is an unfavorable outcome and tail is a not favorable and unfavorable outcome. So number of heads divided by number of trials. This you're saying is a half?
Sir, as the number of trials tend to infinity, it will
As the number tends to infinity?
it will be half. So as the number of trials approaches infinity, this
Number of trials is n, capital N. And now you are saying we take a limit as n tends to infinity?
yes.
Yeah?
I have a slightly different definition. I would say the fact that heads has a half probability, it means that there's an equal chance of heads or tails coming up when you toss them.
That's what you are trying to say. That's a tautology to say that. The probability is the same as chance, right? In that sense, in the sense you're using it.
Okay, but
You toss the coin repeatedly many times, or take a large number of coins of identical conditions and toss them. Okay. Then I agree that the number of heads divided by the number of tails, this is a large number. It's going to become infinity. You're going to take the limit as n tends to infinity of this. This is also a large number. It's a number smaller than n in general. Okay. Now there is no guarantee that this limit exists. Why should this limit exist? If I plot the number of heads and I plot against the number of tosses, so here's n. If I plot the number of heads, it will be a graph in a continuous way. It will keep going. It doesn't tend to any limit. It's not necessary that it should tend to a limit at all. This could fluctuate all the time.
That's the point of defining it as a fair coin.
Fair coin or unfair coin? Unfair coin will give you some number p which is between 0 and 1. The point is it's a postulate. At this stage it's a postulate, right? It's called the law of large numbers. It asserts that this limit exists, that it actually tends to a constant and doesn't go up and down or up and down around that constant forever. There is a mathematical limit which actually exists, and our operational definition of probability, the probability of a head is given by the a priori probability of a head in a single toss is given by the limit as n tends to infinity of the number of heads obtained divided by the total number of trials, tosses. Okay. This is called a Bernoulli process because you go on testing something which has got two possible values and the limit exists. And it's some number between 0 and 1. If it's a fair coin, it's half. So that's our understanding of
Excuse me.
less than equal, just a second, less than equal to 1 doesn't make much sense because if it's equal to 1, it means every toss is a head. And 0 means every toss is a tail. Those are limiting cases. We put it in just for mathematical completeness. Yeah.
So what is the Bernoulli's process?
The Bernoulli process, we'll talk a lot more about it. It's a random process in which there are two possible outcomes. These are Bernoulli trials, actually. They're called Bernoulli trials. All right. Now we understand at some level, intuitively, we understand that the probability exists and it's a number between 0 and 1. Okay. We'll put p equal to half whenever we want to look at a fair coin. But otherwise, p is some number between 0 and 1. Okay. Now I ask, I toss this coin n times or n coins. I take n coins and toss each one of them once and lay them out next to each other. And then the result of the experiment would be something like the first coin showed up heads, then tail, 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 head, head, tail, head, tail, tail, up to some. So it's a word with n letters, capital N letters, and the letters can be either H or T. That's it. Now I ask, what is the probability that the total number of heads equal to H? What is the a priori probability that the total number of heads is equal to H? First of all, we got to find out this capital H is the total number of heads. So I count all the H's in this string of n letters, and that's my capital H. Now, what are the possible values this capital H can take? 0 to n, because all of them could be tails, all of them could be heads. 0 to n. Right? So H takes values in the set 0, 1, 2, 20.
Excuse me, sir.
Yeah.
Can you please repeat the law of large numbers?
Yeah. The fact that that limit of the number of heads, number of successes divided by the total number of trials has a finite limit, some number between 0 and 1. That's the law of large numbers.
So an infinite limit that tends to infinity can
Yes.
also
Yes.
have
Because there's no reason why this thing which is fluctuating, it could not do this forever. There's no reason why it should actually tend to a finite limit.
Can you please repeat that, sir?
You're guaranteed that it does not oscillate above the limit, but it actually tends to a limit, a single limit, well-defined limit.
Yes, sir.
Right? Does the function sine x have a limit as x goes to infinity?
No, sir.
It just keeps going up and down, etc. It's bounded, but it keeps going up and down.
But it oscillates between 0 and 1, right, sir? So we can say that sine
This number
1
will,
of x,
yeah,
1 by
this
x.
number will could oscillate between 0 and 1, or could have a smaller amplitude oscillation. But the theorem guarantees that it doesn't oscillate. It is actually finite.
Yes, sir.
So what is this equal to now? The probability of heads. You need h heads, right? The probability of each head is p. And you need h heads because these guys are all independent of each other. So the probability of 2 heads is p squared, 3 heads is p cubed, and so on and so forth, right up to p to the power h, right? But the rest of them should be tails. And the probability of a tail is q. This stands for 1 minus p. So let's put q equal to 1 minus p. The rest should be tails, n minus h. This is the probability that a particular string of capital H heads and n minus h tails, this is the probability of such a string. But we are asking for no particular order. I don't care what order you produce the heads. So if you had 2 coins, for example, your outcomes are as follows: either tail, tail, or heads, head, or head, tail, tail, head. What's the probability of 2 tails in 2 tosses? 1/4. What's the probability of 2 heads? What's the probability of 1 head, 1 tail? It's 1/4 plus 1/4 is equal to half. Because you didn't worry about the order in which the head appeared. You just said, I want 1 head, 1 tail. I don't care when it appears. Then you have to sum the probability that you had a head and a tail and a tail and a head. This is the problem multiplied because you want a tail and a tail. So you want the word and operates in between. And means multiply probabilities. Here you want a head and a tail. So it could be head first or tail first, which corresponds to these two. So either this or that works. And the moment you say or, you add the probabilities. So when you think about it a little bit, even in common daily usage of language, the word and really stands for multiplication of some probabilities. And or stands for addition of probabilities. This is brought out here. Okay. Which is larger? Head and tail, one, which is more probable? 2 tails or a head and a tail? But the probability of a head and a tail is the same, is equal to 1/4 once again. This is 1/4 and this is 1/4. But the number of ways of doing it is important. That adds up, right? So that's true here too. What should I do here? The order in which these heads appear doesn't matter. I need capital H out of n should be heads, that's all. So what combinatorial factor should I put in? NCH. I like to write NCH in this form. That's the symbol I'd like to write rather than this N choose R. Okay?
Excuse me, sir.
Yeah.
So here we know that heads, right? Sir? So why do we have even the heads? There would be
n minus h tails in the thing.
Yeah.
So why
So
do we have to multiply by this extra factor of q power n minus h?
because of
So
this,
here,
because of this factor. You must look at all strings in which you have capital H heads and capital N minus H tails, in any order possible.
yes.
And it still contributes to your capital H heads. You're trying to count the number of ways in which you can find capital H heads,
Yes.
and that's NCH. Okay? So those probabilities add up. That's why I put this multiplying this factor. The moment you have this many heads and that many tails, this is the a priori probability of any one string with that particular configuration. But there are many such strings, and I have to add them up.
Yes, sir, thank you.
Because it's this or that or this. Once you have this, it excludes this. These are all mutually exclusive possibilities. You must add mutually exclusive probabilities. Now H can have values 0, 1, 2, 3 up to capital N. The total probability, if I sum over all possibilities for H, I should get 1 by conservation of probability. So I immediately require this to happen. You must have summation H is equal to 1 to capital N, P of H equal to 1. The total probability of all possible outcomes is equal to 1. Is that true for this system?
Yes.
Is that true?
No, sir. H can also be, H can also be 0, right?
H can also be 0.
Yes, sir.
Sure, it can.
So if you go from
So if you go from 0, it starts with 0 to N, right?
0 to N. Oh, I'm sorry, I wrote 1. 0. Is this true? We have to check whether it's true or not. So if I sum this, what's this equal to? Does it remind you of something? Reminds you of the binomial theorem, right? There's the power of, you expand what in powers of H? Powers of P plus Q to the power N. P plus Q to the power N, right? So this is guaranteed to be P plus Q. What is that equal to? Q is 1 minus P, so what's this equal to? 1. So that checks. Conservation of probability is valid. Checks. Whenever you use probability, remember you must make sure it's normalized properly. This is called the normalization of the probability, that the total probability is equal to 1, the corresponding random variable.
Sir, if we use a formula for NS4 and HS2, then
Yeah.
then sir, it's not giving halves. Sir.
Then what's not giving a half? Why should it give you a half? These are biased coins. It's not a symmetric distribution.
Oh, okay.
If P equal to Q, yes, what you're saying is right.
Yeah.
But tail and head are not favored equally.
Sir, even if you put P as half and Q as half,
Yeah,
then you get 4 choose 2 into 1 by 4 into 1 by 4,
yeah.
which is not half.
What do you mean?
The entire is not equal because probability of 2. Oh, okay. I got it. Sir.
Okay. This is just the binomial expansion.
Yeah. So
Okay.
now I got it.
Okay. Next, we ask the question, all right, the total probability is 1 for. By the way, what is the random variable here? Whenever we talk of probabilities, there's a random variable. What's the random variable here? No, I give you a fixed number of coins, n. So what is varying? Number of heads. Number of coins I fix once and for all. Number of heads or number of tails, it doesn't matter. Because the number of tails is the number of heads, total number minus the number of heads. Pardon me?
Number of heads. I mean, H is the number of heads, right?
Yeah. Number of heads has got many possibilities. It can be 0 or 1 or 2 or 3 or depending each experiment it can be different. Right? So it's a random variable. It's a discrete valued random variable which can only take the value 0, 1, 2, 3 up to n. Okay?
H is the random variable, right?
H is a random variable. Okay. Next question, if it's a random variable and it's got a probability distribution, what's the mean value? What's the average value? I do this experiment many times and take the arithmetic average of the result. What's the average value? I'm going to denote, how do you denote the average value of a variable?
So within like
You either put an overhead bar or I like to put angular brackets, we'll do that. I need a formula for this. It's the weighted average over this probability. So this is equal to summation h is equal to 0 to n h times p of h divided by summation h is equal to 0 to n p of h. So this quantity h p of h over this sum is the relative frequency with which h appears in statistics. But I take it outside here, it's normalized to 1, so I'm not going to bother about this anymore. So it's h times p of h. Weighted sum. What's the mean square value? What's the mean square value of h? I want the formula. You put h squared. Whatever you want the mean of, you put h squared here. Or h cubed here for the cube value and so on. If you want the average value of e to the power h, you put e to the power h. But weighted to this probability. What is this equal to? Now we're tackling the problem of this. H time. This is not binomial anymore. What is this guy equal to? Each time you want a moment, you need to calculate once again, do some summation, weighted sum, and that becomes very tedious. So I'm going to show you a trick that works everywhere in general cases, and it makes life very simple. It's called the generating function method, and I'm going to use that here now. But for the moment, let me call, for ease of notation, let me talk about it in terms of an abstract random variable x. Suppose you have a random variable x which takes some values. Could be continuous, could be discrete, in some range, it takes some values. Okay? And you want the average value of x. You need the probability, you either need the probability distribution function or the density function for this variable x. So let's suppose you have a continuous variable p of x such that p of x dx is the probability that this x takes values, if it takes values in this interval, it's got some value between x and x plus dx here. And this p of x dx is a curve which looks like this for maybe, and the area under the curve is 1. The probability that it takes values between some x and x plus dx is this area. The total area under the curve is 1, so this integral from the lower limit a to the upper limit b is equal to 1. Because it's a continuous variable, I use a density function rather than a probability distribution itself. This is the normalization condition. Now, if I want the average value of x, I would do the following. Average x equal to p of x times x times dx. If I want the kth moment of x, x to the power k average, this is x to the power k, and so on. For a continuous variable. Yeah.
what exactly are you doing there? Can you explain what's in it? Because it's not
I'll come back to this. I'll come back to this in a minute. It's about continuous variables, but I'll come back to it. It could be confusing at this stage. I'll come back to this.
I don't understand how will P of X always be continuous?
Always be?
Continuous.
No, if the variable is continuous. For example, take the velocity of particles in this room, any one component. It's a continuous variable. The coin example was easy because it was a discrete variable.
Yeah.
Then summations occur. If it's continuous, integrations occur. Because in fact, that's an interesting question. If I have a random variable x, if I have a line segment here, say 0 to 1, and I close my eyes and put my pencil on this, what's the probability that I hit a particular point to infinite accuracy? One particular point, some which I specify beforehand, to infinite accuracy. What is the probability that in a continuum of values you choose one particular specific sharp value? It's 0 because the measure of a point is 0 compared to that of a line. Okay? But the probability that I find a value between some interval and in some smaller interval, that is not 0. That's P of x dx. Okay.
So why is the x there, sir?
Pardon me?
Extra party, why is that there, sir?
Why is that?
Mean of extra party is equal to integral of dx extra party dx. What is that?
Because the mean of any function of x, the mean value is equal to by definition, it's the weighted average of this f of x.
Then what's px, sir?
You multiply by the probability density p of x for each x, multiply the function at that point, and add over all such possibilities, the entire range of the variable.
I'm not getting it, sir.
What have we done here? We have taken this p of x. I want the average value of f of x. So I take the sum over all possible x's, which means integration in the continuous variable, times f at any particular x, multiplied by the probability that you have that x, which is p of x dx, and you do a summation. Integration is just summation in the continuum limit. Okay. We'll come back to this.
So
Yeah.
the denominator we did above, right? Like sigma h P of h of n
That-
running from 0 to n is 1.
Right.
So why do we need to write explicitly the denominator of the average on the left side?
If your probability is not normalized, you must make sure that you also keep this factor. But if you've checked already that it's equal to 1, you don't need it. I like to make sure the probability is normalized in everything I write, so I don't have this denominator. But I have to make sure that it's normalized. We need to tackle this, but let me show you how this is done. 1 second. Consider the following function. Let me call it capital F of x equal to, by definition, it will become clear in a second why I am doing this. But let me introduce a variable x, just an arbitrary variable x, and let me define an f of x, capital F of x, which is given by the summation from h is equal to 0 to n. This is the range over which h varies from 0 to n. The probability that p of h that has the value p of h multiplied by x to the power h. What sort of function is this as a function of x? Why do you say exponential? I'm summing over x to the 0 plus x to the 1 plus x to the 2 up to x to the power n. What kind of function is that? It's a polynomial. Of what order? Of order n. It's just a polynomial function, right? It's a continuous function. It's a polynomial of order n. What is f of 1? It's just summation P of H from 0 to 1, 0 to n. What's that equal to? 1. Because the probability is normalized, f of 1 is 1. What about df over dx? What's that equal to? If I differentiate with respect to x, what do I get?
Summation of NH, which is 0.
Summation over h.
Like in multiplying that with H, x to the power H minus 1.
Pardon me? Derivative of x to the power h with respect to x is hx to the x minus 1.
Yes, sir. Yes.
Normally you use little n for this power index, but I use capital H because I want to talk about the number of heads. What is f prime of 1?
Summation of H.
Put x equal to 1.
H.
That's the mean value. That's the mean value by definition,
Yes, sir.
right?
Yes, sir.
So the trick is to find f of x first, differentiate it, put x equal to 1 and you got the mean value. Okay, so let's find f of x. We know what p of h is, so let's find f of x. So p of h times x to the power h is just this now. What do I do next?
You differentiate this with respect to H.
I combine. This is p to the h, x to the h. So I can write it as px to the power h. That's back to binomial. That's a binomial expansion.
Yes.
Of what?
Px plus q power n.
So this is equal to px plus q. We have to check that the probability is normalized by putting f of 1 equal to 1. But that's obvious. Because you put x equal to 1, you get p plus q to the power n, which is 1.
Yes, sir.
What's now? First, differentiate. So what is f prime of x?
P into n. Px plus q power n.
Is px plus q to the power n minus 1
Into p sub n.
into np. You differentiate this, you get n times this to the n minus 1, and then you have to differentiate px with respect to x, which is just p. So if I put f prime equal to 1, what's this equal to?
Sir, NP divided by P plus Q.
Why should we divide by p plus q? That's 1.
So it's just
They are.
it's just n.
It's just np.
Yeah.
This is called a physical interpretation. If P is success and Q is failure, we are asking what is the probability, mean number of successes in n tosses, right? It's equal to the number of trials n multiplied by the probability of success in any one trial, which is little p. Okay? Very useful formula to have for the binomial distribution. Now you can see that if P is half, it's exactly n over 2, which is what you'd expect on average. If P is 0, it means everything is tails. If P is 1, it means everything is heads. So it fits all those limits. The moment you define this, this is called the generating function for the distribution P of H.
What does generating function mean?
It's generating all the moments. Now I'm going to find a mean square, mean cube, mean everything. It's generating all those moments
Okay.
with suitable derivatives.
Yes.
But of course, if you take 100 coins and toss the coin, it's not that you'll get every time 50-50.
Yeah.
The probability is actually quite low. You can find out what it is. We'll do that in a minute. You can find out what it is. It's not very high. But relatively, it's high compared to all tails or all heads. If I have 100 coins, what's the and the coins are fair. Let's take them to be fair. What is the probability that I get all tails?
One by 3 or
1 over 2 to the power 100. And all heads? 1 over 2 to the, approximately what power of 10 is that? 1 over 2 to the 100.
So it's like 10, I mean,
approximately 30th power.
10 is
About 30, 10 to the power 30, minus 30, right? So you're ending up with the probability, 100 coins, P of H is equal to 100 H 1 over 2 to the 100 equal to 100 factorial divided by H factorial 100 minus H factorial 1 over 2 to the 100. These are large numbers. This guy is a very, very large number. If H is 0 or n, the answer is just 1 over 2 to the 100 because NC0, NC1 is the same. Now we ask what's the probability of 50-50? 50 heads, 50 tails. It will be much larger than 1 over 2 to the 100 because you have to multiply by 150 here. So P of 50, 100 factorial by 50 factorial squared 1 over 2 to the 100. So whereas for h equal to 0 or n, it was just 10 to the minus 30, about 1 over 200, h to 2 to the 100. The moment this factor comes in, it becomes much larger and macroscopic. And if you work it out, and I'll show you a trick to work it out, called Stirling's formula, it's of the order of 8%. 8% is quite a large number, 0.08. That's a large number compared to 10 to the minus 30. This is the reason why when you toss these coins, it's very unlikely that you're going to get out of 100 tosses, 100 tails or 100 heads. You're going to get something in between near the middle for a fair coin. Most of the probability will be peaked around the middle. So if you plot that, it will look like this. Extremely thin, extremely sharp, and extremely thin. And this is around 50. This is exponentially larger than this. Okay. And in fact, if you now calculate, if you say, all right, what about the probability of getting some number of heads between 45 and 55? It's almost 99.999 something percent. Almost always. Exact 50-50 is not very likely. Yeah.
So intuitively, as n tends to infinity, the peak becomes sharper and sharper.
It will become sharper and sharper. Now let's take since he's raised that point, let's take an immediate application of this. We have gas in this room, let's say it's in equilibrium, thermal equilibrium. Let's suppose that the volume of this room is V and the number of particles is N. Let's suppose you have in thermal equilibrium, ideal gas for instance, N molecules of it in a volume V, like this room. I look at a small sub-volume. I look at a small sub-volume here. By the way, N over V, and the mean density N over V equal to rho. The mean number density, the number of particles per unit volume, let's call it rho. So N is very large, V is very large. N is of the order of 10 times Avogadro's number, V is of the order of many cubic meters and so on. N over V is a constant rho. Now I look at a small sub-volume in this corner somewhere here. And let's suppose the volume is little v. What is the possible number of particles that could be in this little v? So let me denote by little n the number of particles. I take an instantaneous snapshot. The particles are all at rest in that snapshot. And I ask, how many particles are inside this little sub-volume v? What's the answer? What's the probability? What are the possible values of little n? 0 to capital N. So it's looking more and more like a coin toss. So little n. What is the probability that the number is actually n? Some value out of these guys. What's the probability that a given particle, any given particle, is inside the subvolume? They're all uniformly distributed. The density is uniform everywhere. So what is the little p equal to? Yeah. So in this problem, little v over capital V is the probability that any particle is inside the subvolume V. And we want n of them to be inside. So there's this to the power n. But you want the rest of the particles to be outside. What's the probability that a particle is outside? 1 minus this probability that it's inside. So it's the. And how many of them do you want outside? N minus little n. Little n inside, the rest of them outside. But we don't care which particles are inside. I just want little n particles in there. I don't care which ones there are. How many ways of choosing are there of choosing out of capital N a set of little n particles? What sort of distribution is this? It's a binomial distribution. What plays the role of capital N is the total number of molecules here. What plays the role of H? Small n, little n. That's the random variable. And this is the distribution. What plays the role of little p?
Small p by capital.
Okay. What's the mean number of particles in this volume?
Small p by capital.
That's precisely the density multiplied by the volume. That's the number of particles. It's exactly what we should get. What's the probability that everything will condense into this little volume V, leaving us to suffocate? It's the analog of 1 over 2 to the 100. It's negligible, completely negligible. But what's the more probable is the fact that it's uniformly spread out, and the possibility of sudden condensation in the corner of the room, even though it's technically allowed, is highly improbable. You can wait exponential of the age of the universe and it will still not happen. Good for us, right? Okay. Okay. This is called the number fluctuations in an ideal gas. You can do other things with it, but we'll come back to this. You see, when I calculate the average of if I have a random variable that's sort of going like this, up and down and in a continuous case, it's got some average value here. But what you really like to find out is what's the scatter about the average. We're very interested in that. We want to make sure that the scatter over the average is calculable should be within our control. If you have wild fluctuations, we should be able to tame it, right? How do I do that? How do I measure the scatter about the mean? What I do is take the deviation from the mean, this minus this gives you this length of fluctuation, and I do that, it can be positive or negative, right? But I want to know the actual magnitude of the scatter. So what I do is take, in this problem for instance, I would take h minus the average value of h, take the square of it, and then take the average.
Yes.
By squaring the deviation from the mean, I make it positive, no negative at any rate, right? And then I take the average. Okay? This is called the variance.
Yes.
It's the average value of the square of the deviation from the mean. And it gives me a measure of the fluctuations. What happens if I take the square root of the variance? If h, for example, in this problem is just the number of heads, but in a real problem with a random variable x which has got some physical dimensions, x squared has dimension of the square of x. But I'd like to compare the fluctuation with the mean value, so I must take a square root of the mean of the variance. What's the square root of the variance called? Standard deviation. Can the standard deviation be negative? Can the variance be negative? No, because it's the average value of a square of quantities. If the variance of a random variable is 0, what can you say about it?
It's a perfect.
It's not a random variable at all, it's just got one possible value. It's not a random variable, it's got a sure or deterministic value. There's a more convenient formula for this guy. This is equal to, by the way, the average of a sum of terms is the sum of averages. It doesn't matter because averaging is also a linear operation, unlike multiplication. So this is the average value of h squared minus 2h times the average value of h plus h average squared averaged. Just expanding the square. That's equal to h squared minus average value of twice h times the average value of x. But 2 is a number, there is nothing to average here, and h is a number, average h is a number. So this is equal to twice h squared plus h squared which turns out to be h squared. Written in this form, it's easy to calculate because it just says take the mean square minus the square of the mean. That's the variance. It doesn't guarantee that the variance is positive definite. That's guaranteed by this. This is easier to compute than that.
So is there any reason this variance is used in reference to the mean deviation which is using the modulus?
Pardon me?
So why is there any specific reason we are squaring and then taking a square root?
I want to know this. I'm not interested in whether the fluctuation is above the mean or below the mean. I'm interested in the scatter above the mean.
You could also use the modulus of the deviation.
You could, but it's not analytic. The moment you use modulus and so on, it's not analytic. Square is convenient, much more convenient. Okay. There are deeper reasons. This is called the second cumulant of the distribution. So there are deeper probabilistic reasons why you do this work.
Swayam Prabha. Digital India. Educated India.